It really is a pleasure to be here in many, many ways. You'll have to excuse me since I only got to bed about 2 a.m. after a pretty hectic few days in Ahmedabad. And I was partially preparing these slides on the very short commute that one has to make to get here from the center of the city. Really is a pleasure. It's just wonderful to celebrate SpeNta Wadia's. There he is. SpeNta Wadia's 65th birthday. Past or almost, approximately. At least, I think it's the 65th birthday in the large N limit. And I was told that I only have an hour or two, so I'll have to be very short in my discussions about SpeNta. I think I have another hour or two to banquet. But I've known SpeNta for a long, long time. And you know, the title of this talk, which will discuss some aspects of this SYK model, was chosen partly because of the fact that it's a very new large N class of theories, which is one of the reasons I am excited by it. And SpeNta and I share a love of large N, and we have for, in my case, for almost, God forbid, 45 years. So that's why I chose this title and the subject of this talk. But SpeNta and I have shared many other things, and one of them is the creation of this institute. And it's just simply marvelous to come back here and see green lawns and beginning to look like what we SpeNta had imagined it will eventually become. This is a picture that was taken, was now 4 years ago, when we were at the site of maybe we were standing exactly where we're now sitting, but it looked quite different. And this picture I find very interesting, because if you look at me, you might notice a bit of skepticism, worry, concern. Whereas if you look at SpeNta, you see a very different image. So I'm going to make it easier for you to blow up. There's me. I think what I was thinking was, oh my God. And if you notice, this person who's looking at me is really worried because whereas right next to me, SpeNta is looking at exactly the same mess. And there he is. Totally confident. Totally assured. You know, positive that it will somehow all work out. And knowing that, you know, he's going to have to invest an enormous amount of effort, diligence, care, love, and passion to make it all happen, but it will. And those characteristics that I just enumerated are what makes SpeNta SpeNta. And so I've been working, trying to help a bit with SpeNta and Rajesh and all of their colleagues to help make this happen. And by golly, it's happened. It exists. And I think realizing SpeNta's dreams. So enough of that. Let's turn, Yeah, it's beginning to look like this. This was the artist's vision of the ICTS before it was built, and it's beginning to look like this. It's really wonderful. So some remarks about the SACHDEV-YE KITAEV model, and that I've been really having fun working on with a wonderful postdoc at the KITAEV, Vladimir Rosenau. So there are actually 3 talks in succession from Subir, from Igor Klebanov, and so in a sense, I'm going to make their job a little easier by spending a bit of time describing the model. What attracted me among the rest to this theory, as I said, is that it's a new class of large N conformal field theories or quantum field theories, quantum mechanical models, the simplest form. It was introduced by Subir and his collaborator as a simple quantum mechanical model of, in their case, the Dirac fermions, but Majorana fermions are equally good with many-body quenched random interactions as a way of getting finding a non-trivial, strongly interacting conformal fixed point in the infrared. And I'm sure we'll hear about the reason why this is interesting and informative for many-body, for strongly interacting many-body systems. Severe. The conformal invariance that was exhibited by the solution, the large N solution of this model, exhibited not just the SL2R conformal invariance, but a full diffeomorphism in one dimension, arbitrary parameterizations of time. But most interestingly, it was a soluble. And that's what's so great about large N limits. They give you soluble classical examples. In other words, large N is essentially a classical limit that can often be solved. And when it can be solved, it gives you a starting point for discussing the interacting theory. And it's absolutely been essential historically in understanding conformal field theories, phase transitions, models of confinement in quantum field theory, QCD, large N supersymmetric QCD, et cetera, et cetera. But as KITAEV realized, this model is maximally chaotic, and therefore probably holographic to an interesting theory in the ADS bulk dual to the one-dimensional boundary, to some kind of theory of quantum gravity, some kind of string theory in the bulk. And since it's soluble, conceivably one can have a non-trivial, although simple as possible in a way. You can't get simpler than one dimension. Well, you can, the matrix model. So the simplest version in KITAEV's formulation is in terms of a Q-body interaction of Majorana fermions, gamma matrices if you want, n of them, with quenched random interactions, the Gaussian variables say. The large unlimited doesn't really matter, everything is Gaussian. But define a self-adjoint Hamiltonian, you want to have a particular quenched random distribution. And then, as in disordered systems in condensed matter, one imagines averaging over, even though in one dimension there's no space, averaging over these quenched random variables, averaging the invariant, SUN invariant, ON invariant variables over the distribution. What SY and K showed was that these models are soluble for large N. They're classical for large N. The scattering, the 2-point function, the 4-point functions, et cetera, all fall off like powers of N. And the 2-point functions, the propagators of these variables are calculable and exhibit a conformal invariance for large times. J has dimensions of mass. And KITAEV showed that they were maximally chaotic. They saturated this bound, which is realized by black holes in quantum gravity and string theory, and probably, given what we know about formally invariant theories, therefore dual to some quantum gravity in 2 dimensions, and presumably in ADS2 as the background. As I said, they are a new class of large N theories. There's somewhere between vector models, where one has an ON symmetry and the dynamical variables are in the fundamental representation, and one only has to sum bubble diagrams with simple geometric series. These are, by now, trivially soluble, but also not that interesting anymore. Although, we've learned that 3-dimensional fixed points of quantum field theories, vector models, are dual indeed to an interesting but strange class of quantum gravity theories, string theories, or the Vasilyev gravity. Matrix models are, of course, have been the most rich examples of large N theories. Their Feynman diagrams are all sums of all planar diagrams. That can't easily be calculated except in special cases. They've been enormously informative about string theory, QCD, quantum field theory in general. In these theories, the example that has been explored by Labanov and Polyakov and many others now, in addition to the standard graviton, whose source is the energy random tensor, you have an infinite tower of massless particles, as in Vasilyev theory. In matrix models, of course, we know there are an infinite number of states, or in the boundary of single trace operators, but there's a limit in supersymmetric QCD where one can achieve a large gap between the dimensions of those operators or the masses of the particles in the bulk, and in the large coupling limit, recover pure Einstein gravity. The SYK models are dominated by what's called Mellon diagrams, and they seem to appear to give rise to a tower of operators, the lowest, most important one being, of course, that dual to gravity, but in addition, an infinite tower, but now of massive particles. Although nobody has managed to construct a model of this type with a large gap. And maybe it doesn't exist. The Mellon models are really the lowest self-energy diagram for the propagator I showed, and then you dress the propagator in all possible ways. They're a very different class of diagrams, different topology, fascinating new direction of large N theory. The large N limit, everything is encoded in the 2-point function, which was constructed way back. And it's soluble in one way of thinking about it, simply because there's a very small and well-regulated set of, well-organized set of Feynman diagrams, these nested Mellon diagrams. So for example, in lowest order, the propagator is modified by this kind of term where the dotted line averages over the quenched coupling, random coupling here and here. And with the appropriate scaling, this diagram, J going like 1 over n to the q minus 3 is finite, whereas diagrams of this type are suppressed by powers of 1 over n. So one ends up with a simple sum of diagrams, which can be, which is written here, where this is a irreducible two-point function, a contribution to the self-energy, and these are full propagators. So the full two-point function, which can be, is just 1 over the free propagator plus the self-energy, and since the self-energy is just effectively a product in position space of free propagators, this gives you a closed set of equations, which in principle can be solved, and certainly numerically, and for small omega, or small energies in the infrared, neglecting this term is simply algebraic and can be solved. So in the infrared, you can drop that and you find a infinite number of solutions of this equation, since you see if you don't have this term, they're invariant under arbitrary reparameterizations of time. So this is diffeomorphism invariance in one dimension, and a particular solution, in fact, for large times in the infrared is just given by a power, as you'd expect. That's also true in the ultraviolet, where the dimension of the fermion field, or the Majorana field, was 0. In the infrared, it flows to a fixed point where the dimension of the fermion field is 1 over 4. That's for a 4-body interaction. For a q-body interaction, it goes like 1 over q. So it's very simple to solve for the two-point function in this theory, much as in vector models. And everything else is constructible perturbations around that classical master field theory. The 4-point function, which begins to teach you about the dynamics of the field, the chaotic behavior, the various operators that have reflections in the bulk, is not totally trivial, but it's given by a linear equation, as is always the case in large n expansions, doing a classical expansion. So the 4-point function is just a sum of ladders where the kernel is given by this diagram and was analyzed by KITAEV, who showed that this theory is maximally chaotic, that out-of-time correlators of the fermion field exhibit a growth in time, which allows you to calculate the Lyapunov exponent, and it saturates the bound derived by Maldacena, Stanford, and Schenker. The operators, the single trace operators dual to the fields or string modes in the bulk, consist of the energy momentum tensor, the operator, and an infinite sequence of fields with higher dimension. And one can explicitly determine what those dimensions are by analyzing that linear equation, the Bethe-Slepiter equation, and it was determined what the various anomalous dimensions were. And that's what you need to construct the full 4-point function. There is an enormous subtlety, however, in the breaking, the explicit breaking of a full diffeomorphism invariance when you choose a particular solution. And that occurs is governed by the energy minimum. There's only really energy, one dimension. So when you go through this game and calculate the scattering amplitudes, the infrared limit is singular. And that is due to a single operator, the operator product expansion, which is in effect the energy. And to understand this model, one needs to carefully control how one approaches the infrared limit. One must introduce a cutoff. It is, of course, present in the theory, in the kinetic term. And it was understood that this kind of breaking of conformal invariance is isomorphic to that Polchinski and Mary found in their study of ADS2, which, again, is a very singular gravitational theory. They had to introduce a dilaton. And there's a beautiful story of how that dilaton in the bulk manifests itself on the boundary as a field, a function of time, which describes the low energy modes that correspond to a continuum, an infinity of small diffeomorphisms around a particular solution. And Adesina and Stanford understood this in the large N limit, in the leading classical, in the large N limit as being described by, and what else could it be really, the Schwarzian of this function. But much is not understood about that yet. For example, that's just the classical large N limit of the effective Lagrangian for these infinite number of zero modes. And nobody yet, I think, knows how to make sense or knows really whether this is completely the right way of defining the quantum theory of these modes. Oops. So anyway, I got into this with Mir trying to generalize this model, find the most general class. We generalized the original model with only n Majoranas to an arbitrary model with many, many families of fermions where the symmetry is broken down. And one can go through the whole game with those time. There is, let me discuss briefly, and you'll hear more from Igor and maybe from Subir about generalizations. There's still a very open question in my mind. What is the most general class of large N theories of what I would call the Mellon-Melonic type, in which Feynman diagrams are given by Mellon diagrams in the leading order of the project. There's a great simplification, and one thing that we did as well as in Stanford is explore the large Q limit. That's where the number of interactions becomes infinite. It goes to infinity. So instead of having 4 body interactions, when it's Q body interaction, it takes Q to infinity. That's often a good thing to do in Potts models and other cases where the large Q limit gives enormous simplification. Sometimes it itself produces a classical mean field theory. The large Q limit, the diagrams simplify even further. Instead of getting diagrams like this, which are melons, you have this basic melon and then you dress it. Here you're only allowed to dress along one cut. So if I add another dressing only here or here or here. And in that limit, there's enormous simplification. There are many other generalizations that have been proposed. Most all of them fall into this general category of the most general set that we formulated with many families. In this case, one has an auxiliary scalar, but it turns out that integrating out that scalar, one gets a 4-point interaction, which in fact is q squared, where this is kind of a supercharged, averaged in an average sense. Obviously, to write h as q squared, which for q is this, you have to average over the j's. There also, this is an example of a higher dimensional SYK that is constructed by Stanford, Gu and Chi, which is a subclass of this generalized model we constructed, where you realize a discrete translational invariance in as many dimensions you want. You can interpret the flavor now as a site on a one in this case, or a d-dimensional lattice, and explore the spatial properties of this non-relativistic higher dimensional Milonic theory. Ed Witten remembered that these Mellon diagrams appear in the literature. Nothing to do with the SYK, original SY model. They appear in an attempt to construct so-called tensor models of higher dimensional geometry. And they yield also Mellon diagrams. So for example, a Hamiltonian involving 4 Majorana tensor fields with indices that run from 1 to n and are contracted in this way as the color flows, generates, as was shown by a community, isolated community, which has been exploring for the last 15 years, these generalization of matrix models or quantum field theories is a way of understanding higher dimensional geometry. These people, this was a discovery of Mr. Giraud, Rivasseau, quantum field theorist, and they were trying to generalize matrix models, which in the large n limit generate planar diagrams and can be ways of discretizing and summing over geometry, 2-dimensional geometries, to 3-dimensional geometry, 4-dimensional geometry, using tensor models to construct path integrals of quantum gravity. I don't think they've been at all successful. As far as I can see, the diagrams they generate are more like some class of higher dimensional geometries, which are sort of dressed branch polymers. Very different than summing in any sense over real geometry. But they've developed a whole enormous mathematical apparatus to deal with such tensor models. And they discovered that indeed they're dominated by these Mellon diagrams, which look like this in terms of the contraction of indices in tensor models, and make it clear that only Mellons survive in this limit. And give you a way, I'm sure Igor is going to be talking about this more, of systematically expanding in 1 over n. This is actually the formula. It's a very beautiful result. What it means is, as far as I know, not understood by anyone. Remarkably enough, this Witten version of the SYK model, although it yields the same Mellon diagrams and the same large n limit, the same classical limit, differs dramatically in the 1 over n expansion. This is very strange. You have 2 theories, one with quench random interaction, one just an ordinary self-adjoint Hamiltonian, both of which have the same large n limit. Therefore, there's a theory with the same classical limit. But the quantum theory is totally different. 1 over n expansion is semi-classical expansion around the classical theory. Now, of course, the SYK model is not, you calculate observables and you average over the spins. So it's not obviously a quantum mechanical theory. It's an average over quantum mechanical theory. You also, in order to calculate precisely, employ something like the replica trick. And as far as I can see, higher orders than 1 over n, that fails. You can't just get there are corrections to the replica symmetric saddle points, which are easy to calculate. So maybe that's the reason you have a classical theory with different quantum expansion. It's very strange. For me, the most interesting question is not so much chaos and whatever Subir is going to talk about as soon as I stop, but what is the bulk theory? It's a string theory, obviously. It's not the string theory of the past or the present, string theory of the future. And since we don't know what string theory is, we don't know what the class of string theories are. Right? String theory just means a guess of what generates systematically in a classical, semi-classical expansion string theories. So I think it's probably likely to be a new kind of direction of constructing string theory. The problem is, of course, that we don't know what it is, and it could be a higher dimensional string theory focusing close to the horizon of a black hole. Could be many, many things. There are many guesses, one and many people have made and are exploring. But we have the theory in the boundary. And in principle, you could reconstruct the theory of the bulk. You believe in the duality, which we all do. But that's not easy, but it is at least direct. And that's what we've been trying to do. It's sort of like, given large N QCD, let's imagine you could solve it explicitly. You try to discover string theory from the solution of the boundary theory. In principle, it's possible. It's perhaps not the most inspired way, but to do that, you first need to start calculating. You know the masses of all the dynamical variables in the large N limit in the bulk. From duality, you need to start calculating interactions. The simplest one is the 3-point coupling of the massive fields in the bulk. That can be calculated from the 6-point fermionic Majorana function on the boundary. And that's what we've just about calculated in a particular limit. This is a very hard calculation. In the large Q limit, these operators greatly simplify. Their dimensions approach canonical dimensions in a very special way. And the 3-point function in the boundary that determines the bulk interaction can be calculated by calculating this diagram, which is a really difficult calculation to do, except in the large Q limit, where it simplifies. And we've been able to calculate, this is an intermediate stage. You still have to do 3 sums. We actually have formulas for the coefficients of the 3-point couplings of this infinite tower of massive fields in the bulk. This is very much like deriving the 3-point couplings of all the gravitational excitations, all the stringy excitations, of which there are many more, in curved ADS2. Now, if you're given those numbers, you then have to guess what you're dealing with is the theory of a propagating relativistic string on a curved manifold. So the next step, even though we've now, I'm ending, calculated these numbers, is to use them to try to derive the string theory in the bulk. I've run out of half my time, so congratulations, SpeNta. And one word of advice from someone who should know: 65 is only the beginning.
I'm used to see this sort of theory where 1/n expansion is different, but the leading order is the same. So it's, to some extent, it happens in matrix models already.
No.
Between, no, random matrix theory of real matrices and complex matrices. The eigenvalue distribution is the same, but one is sort of...
In complex matrices, the eigenvalue distribution is uniform in the unit disk. And for real matrices, it's Hermitian matrices, it's Wigner distribution, which is the projection onto the real axis.
The Hermitian matrices versus real symmetric matrices.
Yes,
so the eigenvalue fluctuation statistics is different. And those are in higher orders in some sense.
No, the eigen...
So you can have theories where 1/n expansion could be different, and they're different theories.
It's rather usually difficult to do, because after all, what is the classical limit? You write down Lagrange, you have a same number of degrees of freedom. You've changed, you have comparing two theories of different numbers of degrees of freedom. And then you write down a classical action, and 1 over h bar in the path integral multiplies the classical action. And you do a saddle point expansion of the path integral.
Well, if you say this is the whole free energy of the theory, maybe it's different.
Now, we know theories now that are quantum field theories that have no classical limit, that are quantum theories that are not the supersymmetric gauge theories, little string theories. So, but it's pretty weird, and I don't really know. I don't think your example is appropriate. I don't know of any example of that. It would mean that it would be very strange. Normally, if we have a classical theory, historically, our understanding of quantum physics was you have a classical theory and you quantize it. And usually there's a pretty unique way of quantizing it. And it would be kind of weird, wouldn't it, if we had, say, electrodynamics, Maxwell's theory, and then there happened to be different quantum theories, all agreeing in the classical limit. I find it very strange. Igor, who is going to talk about tensor model, has an explanation.
If you say the two classical theories are the same, you have to look at all the operators and...
Right. So. And in the tensor models, there appear to be more operators. There are certainly more invariants one could write down that are invariant under this symmetry. But that's one possibility. The other possibility is that it's not clear to me that the right way of interpreting a large N limit of a quenched random quantum mechanical system is in terms of a well-defined quantum mechanical expansion, H-bar expansion of some classical theory. After all, once you average over the couplings, except leading term, it's hard to understand that as a true quantum mechanical